In section 3.2.4, the title the book gave this section was How Can I Use My Equation Solving Skills? I would like to retitle it a little bit, both work, but solving for a variable given another variable. It's one of the ways that we use this. So here's the big question to kind of think about. If I have a rule as an expression or an equation, how do I use that rule to find out something, some information? So we're going to use some real world situation to kind of look at how we use rules in everyday life. Our goals, some things we should know and that we continue to learn. We should learn to use algebraic rules. We should know how to check our answers. We should have an idea of the number of answers or solutions to a linear system when we get to the end. And we should know how to solve equations. Okay, the first question they gave us took us back to John's giant redwood. When we graphed it, we saw that we got a linear equation. All the points were in a straight line, and we decided it was continuous, so we went ahead and connected it. The question is, what are we going to let our variables represent? We've already discussed this, but which one is the dependent and which one is the independent? Does it make more sense to keep track of the number of years planted and use that to find the height, or do we start with the height and then determine the number of years planted? Normally, when we write a rule, we want to think about which one's more logical. If I was a field researcher in this case, I'd probably be keeping track of the number of years after I planted a tree to see how much it grows each year and make some estimates off that. So I'm going to make the independent, or my x, the number of years after planting, and I'm going to let my y represent the height of the tree. So I know what my x and y represent. So now I'm ready to kind of think about how we would write the rule for this. Remember that in the silent board game that we gave you some strategies. For example, if you knew what the value of y was when we had an x of 0, that will tell us whether we're adding or subtracting a certain amount if it's a linear function. Okay, so let's look here. It's a positive 5, so I'm going to start my guess by saying I think I'm adding 5. Now let's look and let's see one of the strategies I gave you. We'll use a different one in the next chapter, but if I'm adding 5 to this as part of this, then I know that these numbers are probably 5 too big. Think about it this way. Some number times a number, then add 5, gives me that number. So if I make this number 5 smaller, let's make it 4, make this one 5 small, this one right here 5 smaller, that would make it 8. Let's see if we can figure out just this part using the numbers underneath. So 1 times what is 4? Well, 1 times 4 is 4. 2 times what is 8? 2 times 4 is 8. So that gives me a good idea. I'm probably multiplying by 4. Let's check the rule on some other points. 3 times 4 is 12, plus 5 does give me 17. 4 times 4 is 16, plus 5 is 21. And 4 times 5 is 20, plus 5 is 25. It also worked for 6. We would get the answer 29. So now I have my rule, and I want you to remember that x represents the height, not the height, the number of years after planting, and y represents the height. So they then took us and asked us this question. How are we going to use this rule? And they gave us a situation. They said that basically John looked and he wondered how tall a tree would be after 20 years of planting. So I've written this down here. So after 20 years of planting, from after it was planted, how tall will it be? Well, we're going to use our rule. Are we going to plug it in for y, which represents the height in feet? Or are we going to plug it in for x, which represents the years after planting? Well, it's 20 years, so we're going to plug it in for x. So we're going to get y equals 4 times our number plus 5. This is the way you've been taught forever to plug things in for x, and so it should feel pretty familiar to you. Let's see, y equals 4 times 20 is 80 plus 5, and y equals 85. Now that's y equals 85, and what does y represent? The height in feet. So this must represent the height, which is 85 feet. So after 20 years, we would expect the tree to be 85 feet high. The next part of the question kind of puts us in a backwards mode, and this should be just a little uncomfortable if you haven't worked these before. How many years will it take for a tree to get to be 367 feet tall? Are we going to plug that in for the height in feet or the years in planting? Well, 367 feet is a measurement of its height, and so we know we're going to plug it in here this time. I know it seems strange not to plug it in for x, because that's what we're used to doing. But we now have a method of solving for x. We've done it many times, and so we're going to go ahead and set it up this way, and we'll be able to solve it. Remember, we're tying this back to what it looks like on the equation mat. And so remember, we want to get all of our x's on one side of our mat, which is separated by the equal sign, and all of our unit tiles on another. I can tell that my x's are by themselves, but I've got unit tiles on both sides. I could move these over here, or I could move this over there. Remember, I need to decide where I want to get my x's. So I'm going to make that decision right now. I'm going to get my x's over here, and I'm going to get my units over there. It just seems easier since all the units are already together. So what happens to 5 positive square units if I move them over here? Well, they flip on the mat, and the flip is represented by a change in sign. So they are going to become -5. I'm going to write this way also because I want you to start seeing that we're doing it this way. If I was adding 5 and I suddenly subtract 5 from the same side, that's going to make that piece 0. Okay, so I've moved my tiles over. What is 367 minus 5? 362 equals 4 x's. Okay. We have 4 x's, so we want to divide by the number that we want to get by itself. So we're going to do 4x and 362. We're going to divide by the 4, because that's what's on the x. We're not going to divide by 4x because we really only want to make this change to 1. So this becomes 1, because that's what 4 over 4 is, and x, because we still have the x on top. 362 divided by 4, I did that on the calculator, and it is 90.5. So let's see what this tells us. This says that x, or 1x, equals 90.5. Well, what are x's measuring? The years after planting. So this must be 90.5 years. Okay, now we have just one little moment before we end this video. We're running out of time. Let's look at our questions for this unit. If I have a rule or expression or equation, how do I use that rule? Well, we use that rule 2 different ways. One way was given the independent variable, we could find out, sorry, wrong piece. Given the independent variable, we could find the value of the other variable, which happened this time to be height. Or if we were given the variable that was by itself, for example the y, we could solve for the x. We had practice solving equations. We didn't check our answer on this one, but maybe we'll get to do that on part 2.